Do you want to just tell everybody what you do first?
My career is I'm a paleontologist. I study fossils. The main area that I study is fossils from about 25 million years ago to the present. My current job is I'm a curator at a museum, and I study there. The focus is on Ice Age animals, so things like mammoths and mastodons and ground sloths. And part of the job is looking at fossils, but most of the job is to do research. So you'll see some of it tomorrow in a presentation, but I come up with questions to research, and I do experiments, or I look at fossils over time. My training is, when I first started in undergrad, I thought I wanted to be a chemist. And I took a bunch of chemistry classes, and it was just too theoretical, like it was basically looking at letters on a board. And so then I thought I wanted to do archaeology, and the first archaeology teacher I had was awful. So that killed that. And I started to take biology classes because I knew I wanted to get into science. And I did really well the first semester in biology, and I was lucky in that they had a program where if you did really well, you were asked to do undergraduate research. And I was lucky because I was kind of shy enough that I wouldn't have done it on my own. And the semester afterwards, they opened it up to everyone. They're like, if you want to do this, you go to a professor. And I would never have done that. But I started to do undergraduate research with this professor who was famous. He's a plant ecologist, and he worked in the Serengeti. And so I got to work with grasses in the Serengeti, and I got really interested in how the animals kind of interacted with the plants. At the same time, I went over to the geology department and started to talk with them, kind of paleontology related, and kind of took that research into the geological world, so much further back in time. And that's kind of how I got into paleontology. I don't know where I was going with this, but just to give you an idea of how long I was in college. I was in college for 11 years plus 2 years of postdoc, so longer than you've been in grade school. I was in college, but it's awesome. I mean, I wouldn't, if you like the career path that you're choosing, it doesn't feel like you're after a certain point. After a certain point, it doesn't feel like school anymore. I'm doing research, and I'm studying things that I want to do. And at a certain point in college, you get to a point where you're taking classes that you really want to take and are interested in. But it does take a long time, and it's basically for what I do, you need a PhD to continue to do it. So it basically is your day pass. You get your PhD, and then that allows you to do the career that you chose. And my degree was out in California, and I got a job back on the East Coast. And basically, you get a job in paleontology, you take a job in paleontology. There's not that many of them. So we came back, which is nice because family is here. So we were kind of lucky in that sense. But, I don't know if I...
Yeah, sounds good to me. You guys have questions? Don't be bashful, right? Remember, science is about asking dumb questions that nobody else is asking, right? I mean, when I say dumb questions, I want them to not be afraid to ask.
So when I first started out, and that's kind of a good, I'll take it if you don't mind.
Help yourself.
My interest, like doing the undergraduate research, I don't know if you have opportunities to do simple research here, but I just started reading, and that's one of the big things that, as a scientist, you don't realize how important, how reading is. You think that's English or language or a subject that you deal with in other things, but 50% of my day is reading 40% of my day is writing, which you don't think about as a scientist, and I was never a good writer. And I still struggle with actually doing it, but that's what my day involves, in reading papers and writing papers, or grants. And the first project is we read a bunch of things, and I was interested in, somebody had done a study where they took a protein from the saliva of like a cow and put it on a plant, and they saw that this one plant grew better. And so they were thinking of, in the Serengeti, does that interaction actually, do plants grow better when they're actually eaten? And to some extent they do. Grasses grow from the base. You have flowers grow from the top, and grasses grow from the base. So the more you mow your lawn, the better the grass grows, right? So it grows as the beginning of the year, you mow your lawn, the grass grows, you mow it some more. As long as you're not mowing it to the bottom, it actually grows better if you mow it at a mid-level. So how does it evolve that way? How does it change to do that? Well, one of the thoughts is that you have these animals that are coming and eating the grass, and they've evolved to do that. So, like you said, it was just a simple thing. I read it in a story. I was like, that's really interesting to me, so I'm going to do that. And I did a little project there. Then when I went for my master's degree, it was the same thing. I actually wanted to finish quick. So we sat down, read a whole bunch of papers, talked with my advisor, said, these are the things I'm interested in, these are the topics. What kind of projects could we work on? And that's how, again, I was reading papers and coming up with very simple questions. And my master's thesis was, just like people come into North America 13,000 years ago, maybe a little earlier than that, but you have many times in North and South America where animals come from Eurasia over the Bering Land Bridge into Alaska and then down. So you have examples. People are worried about non-native species, so introduction of non-native species. Well, I had a natural experiment. You have very many natural experiments of non-native species coming into the continent. And two of those were mammoths. Mammoths first arrived in North America about 2 million years ago, 1.8 million years ago. And then bison come into North America, American buffalo, about 250,000 years ago. So I had two examples of non-native species coming into North America. What I wanted to see is, did they have any effect on the animals that were already here, like horses and camels and sloths? So I look at, my training, besides getting into like the biology, is I had a decent chemistry background. So I look at chemicals in teeth and bones to figure out what animals ate and where they lived. And so what I did is I look at chemicals in mammoths and horses and bison, and did it before mammoths got here and after mammoths got here, and before bison got here and after bison got here, to see if it had any effect on the animals that were already here. So again, it was a simple, I read a little bit, I had this idea, simple question, and you can create a simple experiment to test whether or not there was an effect.
Mm-hmm. I think Mary was finding that literature, we were looking at some of your papers ahead of time, and Mary found some of the terms challenging, I think, right? How do you wade through that when you're first starting out? I mean, these guys are just reading for the first time primary literature.
The part of the problem when writing a paper is you want to be as succinct as possible, because the journal wants to fit as many papers as they can into a specific volume. So the jargon is there because you're using a word that you could use 5 words to make it simpler, but you use 1 word because you want to shorten things and make it more succinct. I think a lot of it is to get just familiar with the paper. Like if you're interested in a topic, get familiar with the papers, and it's continue to read them and look them online. Like I use the word do you guys know what isotopes are? They're chemicals of different weights. So the first time, and unless you go to a chemistry class, you're not really going to understand that. But then understand, the next thing is species names. Like I say woolly mammoth, you kind of understand what a woolly mammoth is. But I say Mammuthus primigenius, that might not mean anything, that's the same animal. So it's just kind of getting familiar with the scientific names, and the common names don't mean anything. We just give them common names just to make it simple for when we talk to newspaper people, basically. But the real name, the scientific name, is Mammuthus primigenius, or for mastodons, it's Mammut americanum. So I think it's
nice
just the
thing about
familiarity of reading, and the other thing is again, I read 5 to 10 papers a day. I mean, again, my job is to read stuff from other people. So it's, in that sense, you're just doing it. Think, if I do 5 papers a day, 5 days a week, 20 to 25 days a year, how many papers that really is, so you just get a familiarity with it. And rather than, at a certain point you're going to understand, and it might take you a little while, you might need to Google specific terms in the beginning, but after a certain point you're going to...
Yeah, it's just like learning to read a foreign language.
Yeah,
right?
yeah.
You know a few words, and you know syntax, and you just got to look up those.
Yeah.
It was a study done probably 20 years ago now, but they say that the first year biology student encounters more new words than the first year language student. I don't know if that's really true. It's educational research, so, but it's a foreign language in a lot of ways. So you just got to kind of get into it and work your way through it. Journal club's a really good place to start. Thursday mornings, there are going to be snakes tomorrow, right? So 7:30 faculty room.
One of the other things too is like if you find there's certain journals that do more or less review articles. Like there's a journal called Trends in Ecology, and if you're interested in ecology and evolution, there's journals called Trends in Ecology and Evolution, where they basically come out once a month and they have a review type paper. So it's 5 to 7 pages, so it's not too long, and it's made to introduce other biologists. So it's still complicated, but it's not. If you look at Science Magazine or Nature, which has short articles, but they're written for a very specific person and a very specific topic, the terminology there is very complicated. But if you start off with other journals that have written review articles, it sometimes is a little easier to get stomach.
So, pop in on the conversation.
What's been your favorite project so far?
I love what I mean, as a career, I love what I do. I think my favorite kind of project, and I do it only a little bit by a little bit because I'm not necessarily an expert, is I'm trying to figure out how long it takes for a saber-toothed tiger tooth to erupt out of the mouth. So the tooth itself is this long. And so the initial idea, and it's like you said, I was doing this research on mammoths and horses. And horses, when they begin, have teeth that are this big. And then over time, today a horse has a tooth that's this big. So one of the projects I did for my PhD was, how does ecology of a horse change over the millions of years when it goes from a tooth that's this size to this size? That was my dissertation. But in doing that and knowing about saber-toothed tigers, they have the same kind of problem. Is they have a tooth. If you look at a not saber-toothed tiger cat, they have teeth that are this big. So what changes are going on from a tooth that's this big to a tooth that's this big? How long does it take to grow? And one of the arguments that paleontologists have made is the tooth is this big. It's basically, if you take a banana and smush it a little bit, that's a saber-toothed tiger tooth. What complication, if it's that big, does it take longer to grow? And if it takes longer to grow, does it have to live with its parents for longer because it can't get food? Because it's taking so long to get out to a functional length, does it take longer to come out? And that was the initial idea, was to see how fast that took to grow. So I used isotopes again. The oxygen isotopes you have in your body are a function of what you drink. And if you're an animal, if you drink from the tap water, it's all gonna have basically the same values. But if you live out in the wild and are drinking from a pond, over the course of the year, the values of the oxygen isotopes compared to a standard change. They get higher and lower and higher and lower. Higher in the summer, lower in the winter, higher in the summer, lower in the winter. So you get this curve. If I sample a tooth from top to bottom, that's over time. And if it occurs over a year or more, you get a curve from summer to winter to summer to winter. And so if you go from summer to summer, that's 12 months. And so if I sampled this much of the tooth, and that's 12 months, let's say that's 10 centimeters over 12 months, I get a rate of growth. So I can figure out how fast that tooth took to grow. In initial studies, I just equated that to eruption rate, but it's not the same thing, because you can have the jaw, the tooth grow in the skull and then just pop out all at once. So now what I'm working on is trying to figure out how long, coupled with how long it took to form, how long it takes to come out of the jaw. And it's been slow. I mean, it's just been you have the CT CAT scan, the saber-tooth tiger teeth, and trying to find a CAT scan machine that's capable of fitting a skull in has been challenging. So that's hasn't been the bulk of my research, but I think has been my most interesting topic.
Why does the fluctuation happen in oxygen?
It's the I'll give you a quick isotope list. It's a function of climate. So you have two oxygen. You guys know oxygen and weights of atoms. So in the nucleus of an element, you have protons and neutrons, and each of those has a weight of 1. For oxygen, oxygen has 8 protons and usually has 8 neutrons. But there's another isotope of oxygen that has 8 protons and 10 neutrons. So it has a weight of 18 versus 16. If your water, H2O, you can be H2, there's many different kinds, but the ones we're concerned with, H2. So you can have water that's H2, a weight of 16 oxygen, and a weight H2, 18 oxygen. If you're trying to evaporate something out of a pond, what's easier to evaporate?
H2 16.
16, because it's lighter. It's easier to give enough energy to make it get out of the pond. So, this is your pond. In the summertime, it's hot, so there's more energy. But you have H2 16Os, H2 16Os, H2 you have evaporation occurring. The evaporation is going to make these leave. So in the summertime, that pond is left with more H2 18Os. And so when an animal comes and drinks in the summer, it's incorporating into its body more of the heavy isotope in the summertime. In the wintertime, you get more rain, and the pond kind of goes back to equilibrium. In the wintertime, it's drinking, and there's more H2 16Os there. If it doesn't get recharged, there's certain places in the United States where you don't get recharged. And one of those places is Lake Tahoe. You guys know Lake Tahoe in California? The values of the water coming over from the Pacific Ocean are more, it just gives you, there's more H2 16O, but they only get it for a very brief part of the year. And there's so much evaporation there that the value of Lake Tahoe is, there's so much more 18O when we compare it to a standard. So when you compare it to something, you just get a value of, it's usually -2 or -4 or -6. So when we look at this signal, this would be summer, winter, summer. But if you look at it on a graph, this is time, this is value. It's usually like -2, -4. So you compare it to a standard, and you get a certain number that we're comparing. The number doesn't mean anything, it's just a comparative number. So when I say it's higher, it's just compared to a different value. But that's why you get more positive values in the summertime versus the wintertime. It's related to the climate. Yep.
Is there a specific geographic area that you found most interesting to study?
It's more of a fascination now, and I lucked into it. I have worked mostly in North America because we live in North America. But I was fortunate enough to meet someone from Spain when I was doing my PhD who wanted to learn the chemistry, and I started to teach her how to do it. And we did a little project that got published, and then basically she was like, I don't really need to do it. You can do it better than I can, so why don't you do it? And I've had the fortune, yeah, it was just kind of a lucky thing, and I've actually now had the fortune of going and digging in Spain. And the neat thing about these sites are Spain has a lot of sites that have Neanderthals in them, and just so things that we're not used to in the United States is the record of humans at sites goes back almost 1.5 million years, where in North America the record of humans being here is only 13,000 years ago. So you have these sites that have 28 humans in one place that were thrown into a pit. And they have animals like lions and hyenas and all the really big carnivores, where in the United States you really don't get those type of animals here. So it's been really kind of cool to be able to work and do digs in Spain and work on that material. But again, it was just something that I lucked into. I didn't go out and seek that. It was kind of thrown into my lap. Yep.
What would you say is the most difficult part of your job?
Writing. I can say that. And then I think I liked science initially because I didn't have to do it. And I don't think that they teach, well, at least when I was in high school and going even through undergrad the first couple of years, it was more terminology based and answering questions. And my makeup isn't to be able to write really well. I just had always struggled with it. And so to actually there's two problems. One is I'm not very good at it. And then there's a certain point where you're not motivated to do it, because I came up with a question, I did the experiment, I got the answer, now I'm done. I know the answer. Nobody else knows the answer, but I know it, and I'm ready to move on to that next question. But part of my job as a scientist is to write it down so other scientists know. And so you really have to get motivated enough to write, and then to actually publish a journal article it's hard. And you send it into a journal, they send it out to what they call your peers, but it's other reviewers in the same field who are there, and they can be very nitpicky about, did you use the right statistic? Did you sample enough animals? Does your data follow your conclusions? A typical paper from start to finish will take at least a year from when you submit it to when it comes out, and it's usually longer. My paper that I just published a paper, it just got accepted. I first submitted it in 2009. So my next paper to come out, it's taken that long to go through the journal process. It was reviewed 3 times, and each time they sent it to different reviewers, and each time those reviewers had different problems. And one of the things I was actually, it's on saber-toothed tigers, and I was modeling the diet of these. Were they eating mammoths and horses, or were they eating deer and things that lived in the forest? And I did one model, and then the reviewers suggested I do another model. I did that model, and the next set of reviewers suggested I do another model. I did that model, sent it in, like, well, that's great, but you should do this variation of this model. So finally, and each time you fix it, so maybe it takes me 2 months to fix it, and I send it back in. The review process is 6 months. And then you get it back, and I fix it for 2 months, you send it back in, it's another 6, so it can take a really long time. So I think the hardest, for me, the hardest thing is kind of getting down to writing it, whereas I had the answer. I satisfied myself in 2009. So the research that I'm doing now is so far beyond that
It's no longer current.
it's no longer current to me, but it's important that I get it out so other people know what's going on.
Plus, I know hiring and retention decisions a lot of times depend on what you published and
Right.
how frequently you published, and that's what they pay you for.
Right.
So, is that true with the job that you're at right now, or is that more?
My job, I'm a curator at a museum up in Albany. And they want us to publish, but the majority of the job is they want research going on, but curation, making sure the collection is good, is more significant. But for me, getting a certain number of papers out a year is important, because maybe
Intrinsically important.
yeah, maybe the state doesn't want to have a curator of paleontology at a certain point.
Yeah.
And so I need to keep up my resume good enough to be able to get a job somewhere else. And if I just stopped writing papers, I would never be employable. And it depends on where you are, and if you have students, if you have graduate students, sometimes it's easier to get more publications. But I try and shoot for 2 or 3 like first authored papers a year, so it's kind of I have probably 6 or 7 going, and then you finish one, send it off, and you start the next one, send it off. So you're always writing, and it's just part of it. And then grants, if you want to write a grants to, let's say, the National Science Foundation. If you do a good job, it's going to take you a month to a month and a half of just sitting down and writing that grant to ask for money so that you can do your research. And the funding rate for the place that I send is like 5%. So you work on it for a month and a half, kind of knowing that you're not going to get it, but you hope over time that if you keep sending it in, that it'll get funded at a certain point. But that's kind of hard because you're dedicating a month and a half to something that you're pretty sure you're not going to get. But it's part of the job, and writing has been the hardest thing, but something that if you know it now, get used to it.
So you said that when you started college, you thought you might want to be at first a chemist and then a biologist, but then eventually you got into what you do now. So if you look back at like your early life when you were in high school, even before what your parents did or whatever, do you see anything that might have influenced your decision to do what you do now?
Yes, and the only reason is because my parents bought property in a rock quarry. So and the first few years before we had a lawn, they brought in topsoil that was just full of rocks, and I used to just love going out and smashing the rocks and seeing if there was something inside. There was never any fossils, but it was always kind of a fascinating thing to me to do. So I think that was kind of an influence, but I could have seen myself being a chemist. I think if I had really good teachers, like if I had a teacher, like the anthropology thing, I was certain I wanted to be an anthropologist, and if the teacher was any good, I probably would have kept on going, but the teacher was so bad that I just couldn't stomach taking another anthropology class. The thing that I think helped me is I knew what I didn't like rather than knowing what I wanted to do. So when I first started, I was like, well, I know I don't necessarily like physics, but I took physics, but I kind of steered, let's try chemistry. And I took chemistry and I didn't like it. So let's try anthropology and didn't like it. Tried biology and I knew I liked